Yes. All right, everyone, welcome to the 5th seminar lecture in Seminar in Computer Architecture lecture. And we will start with sector DRAM. Lawrence will present this work. Lawrence is a master's student in computer science, in his second to last semester, and he is really interested in computer architecture. That's why he took this course.
Yes, indeed. No, I major in theoretical computer science, but there's this thing called credit requirements. Okay, so hi. As Atabek already said, today I'm going to present a paper on sector DRAM, a practical, energy-efficient, and high-performance fine-grained DRAM architecture. The way this talk is going to be structured is I'm going to give you a quick executive summary and highlight the motivation of the paper. Then I'm going to explain how DRAM normally works, both how it's hierarchically organized and the commands it uses. I'm going to highlight some inefficiencies in those, and then I'm going to show you how the paper approaches improving on those inefficiencies. Then I'm going to explain how DRAM usually transfers memory between the memory chip and the processor, and also going to highlight some inefficiencies in that process, and then going to show you how the paper tries to improve on those inefficiencies. Then I'm going to talk a bit about how these hardware changes that the paper proposes are integrated into the wider system, some of the challenges that poses. And then I'm going to highlight which improvements the authors achieve with the paper, with the techniques implemented in the paper. And I'm going to talk about the strengths and weaknesses of the paper. And then at the end, we can have a discussion about the paper. Okay, so first, an executive summary. So what's the main problem that this paper tries to address? Well, many modern programs have very low locality in their storage access, which means they don't go through large contiguous blocks of memory, but they sort of jump around, which clashes with the way DRAM is organized, which is very coarse-grained. DRAM activates storage in rows, which are typically 8 kilobytes large, and loads memory into cache in cache blocks, which are typically 64 bytes large, which is an issue when words are usually 64-bit, so by a factor of 8 smaller large. The goal of the paper was to design a fine grain, so something that goes at this in a smaller way, low cost and high throughput DRAM substrate. The key idea is the way it achieves this is by small modifications to the memory controller and the DRAM chip. It activates really small, physically isolated regions of a DRAM row instead of an entire DRAM row, and it transfers sub-cache block size data in variable burst lengths. The key results achieved by the paper are for memory-intensive workloads, sector DRAM improves the energy consumption of a system and improves the system performance, and does so with very small energy and area overhead. And there are some other approaches that have a higher performance increase, but they use significantly more energy or area. Okay, so next, what is the key motivation? I already kind of alluded to this in the executive summary, but to highlight it again, typically memory access is a cache block granularity. So when we load something into memory, we load an entire cache block into memory. That's into the cache, that's 64 bytes. But data operations in assembly and stuff are at word granularity, which on a 64-bit architecture is only 8 bytes. And on average, less than 60% of a cache block is actually touched by a modern process. So like the extreme case would be, so we have 8 bytes, 64 bytes, only an eighth is touched. That's not how it actually works in practice most of the time, because there is some locality, but less than 60%. So a considerable amount of cache blocks are loaded into memory, but never, data in a cache block is loaded into memory, but never actually used in memory. So there is unnecessary data activation and movement through all steps of the DRAM process, basically. And we want to avoid that because inefficiency is bad. Previous approaches to the problem all either use very large area overhead or only improve parts of this process. And this paper aims to sort of improve everywhere, basically, and do so with less area overhead. Okay, so before I talk about how this paper or the authors propose to modify DRAM, let's first have a look at how a modern DRAM chip is usually built. So a modern DRAM module, the thing you put into the back of your PC, is made up of several chips. Each chip is made up of usually 8, but it could be another number, several banks. And I'll go through this a bit quickly. We'll go through it in more detail when we tackle how certain parts of the system actually work. Each bank is built up of some logic, global row decoder in this case, that and is split into several subarrays, and each subarray is split into several mats. And mats are sort of the smallest organizational unit that we really care about. But to look inside of a mat has some internal logic as well, and is basically a large grid of DRAM cells. And a DRAM cell is basically just a capacitor and a transistor that controls access to that capacitor. So when this transistor receives energy, then the capacitor is connected down to these sense amplifiers, which can sense the storage in the capacitor and then make it accessible for us for operations. Okay, so how do we interact with the system? Well, there's basically 3 important commands/steps to interacting with DRAM memory. But before we can read or write to any part of the memory, we first have to activate it, which that's an activation command that sends a command to a specific row of memory and basically connects those to the sense amplifiers. We'll go through that in detail in a second, and makes it available for use, both for reading and writing. Then we have read and write commands, which basically do what we would expect. This is not the version of the slide I thought it was. Something weird happened, but so be it. So we transfer data between global and local row buffers. And then the final step in sort of the life cycle of a memory row is the pre-charge command. When we want to close a row, when we're done with the row, we send a pre-charge command, and we need to do this before we can activate a different row. So we can only have one row active at a time per bank, and at the end we send a pre-charge command. Okay, so let's have a look at how these commands actually work. So first things first, an activation command. So when we send an this is a new, I don't know. So when we send an activation command, we send it to the DRAM chip basically, and the I/O logic of the chip decides which bank we want to activate a row on. That information is then passed on to the global row decoder, which, based on the most significant bits of the command, finds out in which subarray the data we want to look at is located and passes on the rest of the command in each subarray. So it's sent to the subarray and to every mat on that subarray. In each mat, the local row decoder decides based on the less significant bits of the command which row of data we want to access, and then basically activates that row by sending a signal to that row. And as we discussed above, now these transistors basically get energy, which means the information is propagated down to the sense amplifiers, and they store this information for our use, basically. Okay, so now that we've activated a row, how do we read from write to a row? I'm going to go through this on the example of a read command. Write commands function very similarly. Some things go in a different direction. It's not that important for what the paper does. Okay, so once again, we issue a command to the DRAM chip. It goes to the right bank. And then instead of going to the global row decoder, it goes to the CSL or column select logic, which sends a signal to every mat in the activated row. So this goes through all subarrays, but only one row of these has been activated. It's only loaded into one sense of local row buffers. And from those specific local row buffers, it selects one or several sense amplifiers, and the information that is stored in those sense amplifiers is then propagated down to the global row buffer, and then it can be transferred through the global row buffer into to our processor. And writing basically works the same way, only that some data goes in a different direction. Finally, we also have a pre-charge command. This works exactly the same way or not exactly, works very similar to the activation command. We won't go through this in detail. It closes the row, and important for us is basically also that it has some free information, that have some free bits in the command that isn't used there. Okay, so you might have already noticed this maybe, but there are some inefficiencies in this that I also alluded to earlier, and that's that we only often use a small part of a cache block, but we activate a huge part of memory, even more than a cache block, and then we load, we read and write only at cache block granularity, so we spend a lot of energy activating and moving around data that we never care about. So specifically, what if we only care about, so usually cache blocks are spread across chips. What if we only care about the first word and then some bytes at the end? Well, we still activate the row here, and we still read and write to that row, even though we never use this data. So that's bad. And not only does that waste energy, it actually even affects performance, because there are some timing constraints built into DRAM that, because activation takes so much energy, we can only do a select number of activations per certain time increments. The exact specifics depend on the chip and stuff. But basically, so that we can be sure that activations actually work, we have to limit how many of them we can do. And that is mainly because of the large energy costs of activations. But what we might notice is that conveniently, these DRAM rows are already kind of split into lesser organizational units, specifically the mats. And this observation is something that the paper tries to use to develop something that wastes not no energy, but less energy. Okay, so the mechanism proposed by the paper is called sectored activation. And what we do is, for every DRAM row, we isolate the mats from the master word line or global word line by adding in some extra local drivers. Is not that important. Basically, we don't activate them. In the normal DRAM architecture, we sort of have activators that go onto 2 mats. We now make sure that every mat has its own local drivers. And we add 8 sector latches that isolate these mats from the word line, so that so we have these transistors here, basically, that information is only passed down to a mat. So an activation command is only able to get through to a mat when that sector latch is set to 1. So those are the, okay, I think now it sits better. Yes. I hope people were able to hear me before. Okay. Yeah, so if we add these sector latches, we also notice that we have to have some way of like controlling these sector latches. Otherwise, there's no point in them. So we also have to do some things for the memory controller. And that is one thing, we add additional information to the precharge command. So that so we add 8 extra bits that basically define for the row that I activate now. I only want the next row that I activate. Sorry, precharge command closes the previous row. For the next row, I only want to read and write from and to these sectors. And we also are able to modify internal timing constraints, which allow for more activations. Specifically, how that works is a bit more complicated. But basically, when we send a less intense, we modify the timing constraints so that when we send an activation command that only activates 1 sector instead of all 8, then we're allowed to do more activations in less time again. But there's like a whole bunch of different timing constraints, so we won't go into more detail than that. Okay, so yeah, so basically we have these extra sector latches, and those mean that we only activate a part of the DRAM row if we only want to read to write from other way around a certain part of the DRAM row. Okay, so next thing, okay, so we load these, so we activate less and we spend less energy for reading and writing, but we still have to tackle a different aspect of how DRAM works, and that's the transfer of information between the DRAM chip and the processor or the cache. So here's how this works in default standard DRAM. We have an entire cache block. We spread that out over several chips and over several mats. But the way we transfer it is basically in what's called a burst. That's a burst of transmission, 64 bytes long, so 1 cache block long, which is split into a fixed number of 8-byte beats. So in this case, 8-byte beats each cycle of the clock, or each half cycle of the clock in this case, but each cycle, basically, we send 8 bytes between the DRAM chip and the processor. Always 8 bytes, always 8 beats, so 64 bytes in total. And each beat is distributed between chips, and basically we spread it out in such a way that we can draw 1 byte from each chip per beat. And the transfer happens on cache block size, which once again is bad because we don't want cache block size, because as we said, less than 60% of a cache block is actually touched by a process. So if everything happens in cache block size, then some of the savings, this is bad for us. We want to transfer less because this wastes time. Every 8 bytes that we send more is 1 beat longer, which means more time and more energy, of course. So how does this usually work? Well, we have a transmission queue between the DRAM chip and the processor, and this is usually sort of controlled by a beat counter that counts up from 0 to 7, which decides which parts of the cache block are being transmitted at any one beat, and that's implemented both by the processor and the DRAM chip. So we have a counter-based circuit, that decides which bytes to transmit in a beat. And what we can maybe notice now is that we already have a sort of system in place that that decides which parts of the cache block are transmitted at any one beat. And the paper now tries to leverage this system to, once again, reduce inefficiencies via a process that's called variable burst length. So what we do is we replace the counter with a circuit that takes as input the sector bits that decide which sectors we want to read to write from. The same way it works in the pre-charge command. And what this circuit then does is it skips all beats where we would transmit information that's stored in sectors that we didn't even activate. Okay, and this leads to a reduction in the length of bursts most of the time, and also in the transmission costs in form of energy, of course. Okay, so there's some extra housekeeping that we need to do around this, because that this works is we need to both the processor and the DRAM chip need to know which part of the information is transmitted when, so that if the processor would expect a normal 8-beat burst, then obviously it would get wrong information in wrong places. So we need some extra housekeeping to keep track of this. So the sector bits define the length of the information, and that's already passed through every part of the system. But we still, so we need the extra circuit that I showed before that, depending on the sector bits, determines which beats we skip. We also need some extra, like we need an extra counter circuit and stuff like that to keep track of what is transmitted when. In total, it comes down to 34 logic gates and 128, I always say this wrong, bits of storage. So not much, but some extra overhead. Okay, so now this is basically how the DRAM chip is modified, but that is no use to us if only the DRAM chip is modified. We also have to modify the system around it, because if we have a system that always sends load requests for full cache blocks, then the fact that our DRAM supports load requests for half cache blocks doesn't help us at all. So we actually need to integrate this into the wider system. So we also have to change how the cache works. So what we do is, instead of just having a normal cache block, which has 64 bytes of data and a tag for cache protocols, we add a bit of overhead. We add 8 bits, so 1 bit for each word. A word is 8 bytes in the cache block that determines whether this word is valid for this cache block or not. So I add 8 validity bits, and we also need to add these 8 bits to every load and store request that we send to the DRAM chip, because we need to tell the chip which sectors we actually want to load from and which we don't. Okay, so this poses some additional challenges to any system implementing this. Some of you might have already noticed which, and that's specifically the idea of sector misses. So if we try to access a cache block in the cache, then normally there's two possibilities. Either we have a cache hit or a cache miss, which means that specific block is loaded into memory or it's not. Well, this introduces a new type of cache miss, basically a sector miss, which is we try to access information that is in a cache block that's loaded into memory, but in a non-valid word. So we try to access a valid cache block, but an invalid word. This is bad. This leads to a cache miss when previously there wouldn't have been a cache miss, which decreases performance. We don't want that, which is why the paper introduces two key mitigation strategies to sort of prevent this type of sector miss, or to reduce this type of sector miss. They don't manage to completely prevent it. So one is load, store, queue, look ahead, and one is sector prediction. We'll go through both. First of all, the first strategy to mitigate sector misses is the load, store, queue, look ahead. And that is normally load and store instructions don't happen one by one. We have sort of a short queue of load and store instructions. Of load and store instructions. So here we have the added sector bits for every load and store instruction. What we try to do is if we have two load instructions or store instructions for the same bit, for the same cache block in this queue, but for different sector bits, then we don't have to actually have to load both of them. We want to make sure that when we load it the first time, we load all relevant sectors so that like these very preventable sector misses don't happen. So the way we do that is we introduce so first of all, as I said, we augment all of these by sector bits, but we also introduce like a small extra circuit. And what this does is it basically, whenever we add a new load instruction, we go through all other load instructions that are already in this queue and or the bits. So let's say we have one load instruction up here that just wants to load sector 1, and we have one load instruction that comes in new and wants to access the same cache block, but just wants to load sector 8. Well, then when we load this first time, we immediately load sector 1 and 8 because we know we'll have to otherwise have a sector miss later. The problem with this is that it would be super inefficient if this LSQ was very long, because all of that time is basically the processor waiting on data it needs. So this queue is usually very short, and we can't prevent all misses with that. So we introduce a second technique, which we call sector predictor, and the basic idea here is basically whenever we already access the cache block, we access certain sectors, and that probably informs which sectors we'll access in future. So whenever we have a cache block in memory, we keep track of the currently used sectors. So whenever we access a sector, we set these bits to 1. And whenever we evict this, whenever we evict a cache block, we keep track of this information also in a sector history table. And there's some complicated logic. There's a table index and how we access that and stuff. But the basic idea is we keep track of which sectors we've already accessed. And when we next load that same cache block into memory, we look at this information and say, well, last time we had this cache block into memory, we looked at all sector bits, so we might as well load the entire cache block into memory this time. The second thing we also keep track of is for any instruction, there is an assumption that they usually try to access the same parts of a cache block. So if we have a for loop that goes through a bunch of data and always does the same operation, it's probably always going to access any piece of data it looks at the same word offset. So we keep track of that as well, and also store that information in a sector history table, and also consider that for future operations. And whenever we load a block into memory for one of these operations, we keep track of that information as well. Yes, okay. It says the things I just said there. Yeah, okay. So these are the two strategies we try to prevent sector misses. We'll now have a look at how this entire thing comes together, what sort of results we achieve. First, a quick look at the result methodology. I won't go through this in detail. This is more for people who really care about this. They can have a look at it. the authors use a bunch of different simulation estimation tools. They have a very thorough list of what they use for what and which workloads they use. They compare their performance both against just the baseline, so the normal DRAM implementation, but then also some other fine-grained DRAM mechanisms that basically operate off the same core idea. Once again, I won't go through the details of these because they're not that important in their whole papers in and of themselves. It's only to give some extra context to the figures we'll be looking at later. And they also, yes, look at a bunch of workloads from a variety of like workload data sets. And they also extended these to several, from 1 core workloads up to 16 core workloads. Okay. Yes, so these are the workloads, the benchmark sets, in case people here know them. I didn't, but yes. Okay, so the first thing I personally thought was interesting is, okay, so what's the downside of the system? So we said sector misses are something that happens, so some quick information about this figure. So here on the y-axis, you see the different workloads, and on the x-axis, you see the number of cache misses. And the gray data is the complete baseline, so just normal DRAM. And then the orange data is sector DRAM without any mitigation strategies, so no look ahead and no sector prediction. And then all of the other colors represent variously intense versions of these mitigation strategies. So a couple of things to highlight. First of all, especially sector DRAM, the baseline, increases cache misses noticeably. So we have a lot more cache misses. Of course, single cache loading operations are also less expensive, but we also do have significantly more cache misses. This is bad. Secondly, the mitigation strategies we do have are actually quite effective at reducing the cache misses we have. And the one other interesting takeaway from this is, as I said, all these colors represent differently strong versions of the mitigation strategies. The dark blue one is look ahead with 2048 entries of LSQ, so of a load store queue, so a really long look ahead, as the sort of queue that would be completely impractical. And what we can see is that this does not perform significantly better than something that only looks ahead 128 entries, but has a stronger implementation of the sector prediction. So this is worse. Or even something that looks ahead only 16 entries and has the same strength of sector prediction. So this is worse, but it's in the same order of magnitude bad. So what this shows is that the mitigation strategies we have are somewhat effective. So this sort of look ahead is we'd have to develop very good predictors to be better than that sort of look ahead. What this does mean is that sector DRAM does have worse performance on some workloads. Okay, but enough of the worst case. Let's look at the normal case. Here we have a bunch of figures. The right column represents low memory intensity. The left column represents high memory intensity, and the middle is medium memory intensity. And what you see here is in light, you always see the performance of the baseline, and in this darker red, you see the performance of the of sector DRAM, sorry. The x-axis represents the number of cores, and the y-axis is in the upper diagrams, it's the speed up. Higher is better in that case. And in the bottom set of diagrams, it's the energy use. Lower is better in that case. And what we see for high memory intensity, sector DRAM performs consistently better with consistently lower energy use. And this improvement gets better the more cores we have. And for low memory intensity, it's more complicated. But for instance, so there either is no improvement or there's even sometimes worse performance of sector DRAM. So like, for instance, in this case, sector DRAM uses more energy than the baseline implementation. Yeah, so sector DRAM has issues with low memory intensive workloads and consistently outperforms for memory intensive workloads. And this performance gain, or in general, the comparison tends to get better the more cores we look at. So one thing we looked at is that the authors also implemented is to offset this performance decrease for for low memory intensity is they developed a strategy they call dynamic switching, in which case, under some conditions, sector DRAM is turned off. And what you see here is 3 diagrams that compare in dark red the dynamic switching policy, and in orange the always on policy, so where sector DRAM is just always on. And you only see these two compared to each other. What you see is for low memory intensity, dynamic is basically at a normalized speed up of 1. So it's basically as good as just no sector DRAM. And for what this does mean is that and it also performs better for some versions of medium memory intensity. What this does means it sacrifices some performance for high memory intensity workloads. So this is a way to mitigate some of these weaknesses, but it brings its own drawbacks. I keep forgetting doing these. Yes, so there's a dynamic switching strategy and much better performance at low memory intensity, slightly worse at high intensity. Okay, so now the power results in general, this was one of the main things that the authors cared about. Power improves consistently. So what we have here is diagrams that measure the power draw, the maximum power draw for activation, read and write commands, for commands that read 8 sectors, so basically just a normal cache block read, and all the way down to only 1 sector. So basically the maximum application of sector DRAM. And on the bottom, you see how much energy these things draw. So energy is consistent power draw, basically, or how is power times time, basically. So what you can see is that the biggest improvements are for read and write operations, but the biggest improvements are generally in DRAM array power, so not in the transmissions and stuff like that, but in the actual energy required to keep up the state of the system. And you can see big improvements for read and write, but the energy consumption actually decreases quite strongly here because this, the y-axis is different here. So this is 4 times as large, and this lower power and energy consumption allows for some higher higher activation rates in the manner I just discussed before. The details of like how exactly the time constraints are changed are found in the paper, but it's important to keep note that this actually also affects performance. Yeah, okay, so then area, this was another thing the authors cared a lot about. I won't go through all the details here. So I already at every point tried to address how many extra sector transistors, latches, and wiring you need. The general result using cacti as a estimation tool was that the area overhead is around 2%, or no, actually less than 2%. So 1.27% of the chip area, which especially compared to half DRAM is quite a bit better. Okay, so then one final result slide is a comparison with other state-of-the-art fine-grained DRAM approaches. And what we can see, I won't take you through all of these, so it's once again the relative speed up of different approaches. The lightest one is sector DRAM, and at the top we have the speed improvement, and at the bottom we have the energy. And what we can see is that most of the time, especially if we look at the mean improvement, sector DRAM performs better than the other approaches, except for half DRAM, but in an energy, sector DRAM is almost always the best performer, or actually for these always, no, there's one workload where it's not the best, but it's almost always the best performing implementation, and it still has a lot less energy draw than half DRAM. Yeah, so approaches perform better than most, but you definitely use much less energy than all of the comparison points. Okay, so this was sort of the aim of the authors. They wanted to implement something that had a high throughput with a very low area overhead, and changed both the activation and the data transform. That's both the sectored activation and variable burst length that I introduced earlier. It's not the fastest approach, but it marries good energy efficiency and area conservation with consistent performance increases. Okay, so I hope you now have an idea of the paper. Final point is the strengths and weaknesses of the paper. So for strengths, I think it had very comprehensive explanations both for how base DRAM usually works and how all of their modification works. This was very helpful for me because I didn't have to, like, I think it was very readable in a way for even for someone who I have a very foggy memory of how DRAM works, or I had one before I started reading this paper. It also has very low area overheads, which is something the authors cared a lot about. It also has, especially when I compare this to some of the presentations we saw earlier, where a lot of the people sometimes complained that how the speed up results were estimated and how the estimates were put against other implementations that try something similar. It has a very robustly explained simulation methodology and which data sets it uses. I already had a lot of result slides. There's like far more information in the paper. And it also leverages existing structures of DRAM. So it tries to basically work within the existing framework, not introduce something completely new. And I also like that it analyzes basically every aspect of the implementation. It cared about area, about power consumption, about performance. Yeah, so basically most questions one could have about the implementation were answered in the paper. Now for weaknesses, I think one big weakness of this is that it doesn't only need modification of one part of hardware, so it doesn't only need to modify the DRAM chip, it also needs to modify how the processor works and how processor caches work. It is also only better than competitors under a very specific set of constraints. So I personally can't assess how valid these constraints are, but I wasn't really sure that half DRAM's 2.6% area increase is that much worse than sector DRAM's 1.7% area increase. So it is, if you said like 2% as a dividing line, which the authors did, but that might also be self-serving. I don't fully have the capability to assess that. There were also some inconsistencies in the paper, mostly in graphics, about how some terms were used or how certain architectures were shown. And then when the modifications were shown, it showed something differently. I think this was because they took some of the graphics from other papers, but yeah, that was slightly confusing to read. I also thought that maybe sector prediction implements basically a form of prefetching, and this seemed like an avenue for certain side channel attacks, and that was not addressed in the paper. I know that a lot of other architectures also do some form of prefetching, but still I would have liked to have that addressed at some point. And there's also the fact that for some workloads, sector DRAM actually performs worse than the baseline, which when we're going to modify everything is bad, in my opinion. Hot take. Okay, so that's my presentation of the paper. We're gonna, oh, wrong button. We're gonna come to a discussion. But first, yeah, if in case you have any questions, I can answer those, and then we can sort of go over into a discussion if that arises naturally, and if not, I have some jumping off points for discussion. Yes, so questions. Yes.
I don't know if you've addressed it already, but right at the beginning, you said with classical kind of the RAM, the cache sizes, around 60% or less than 60% is actually of the data is actually used. Do you know how that percentage changed with these new adjustments?
I don't. I don't know actually. So like if we just do DRAM without any mitigation strategies, then obviously it's going to be 100% in normal cases because we only request. But I don't actually know how sector prediction, loads to queue look ahead shouldn't affect that number either, because there we only load things which we actually will need, which are already in the queue. But I don't know how sector prediction affects that. So no is the answer, but yeah, so a lot of these things don't affect that, but sector prediction could also, will change that. A lot of these modifications will leave that number at 100%, but sector prediction will also load things into memory that we don't need. I don't know what that percentage is. That 60% figure comes from a different paper. So they didn't, so this is not like an inconsistency of the authors. This was just to like provide the motivation, but it would be interesting to know. I don't think it says so in the paper. I can't swear to it, but okay, yeah.
Okay, thanks.
Is anyone also keeping track in case there's like questions in Zoom? I don't know, or do I have to? Okay.
A question about the workloads used for the when the sector is confronted with the baseline.
Yeah.
I think we showed before that sector DRAM works better when you have memory-intensive work.
Yeah.
So are all the workloads used when we took the average and we showed that on average it works better than the baseline or memory intensive?
So no, we have like we usually have this split into so for instance these I think so usually we have this split into categories of like high. So for instance, this one is maybe this one is a good yeah. So in case the microphone wasn't on, the question was like whether the performance measurements were all done on high memory intensive workloads, especially when we looked at the average. The answer is no. A lot of so maybe some of the things I showed were mostly for high memory intensity, but this one is, for instance, one figure that isn't. So these are just low memory intensity workloads, and what we can see is this doesn't show the baseline in here, but the baseline is going to be at 1 because that's how relative speed up works. And what we can see is for low memory intensity, the speed up of sector DRAM is below 1. For the average, that's a complicated question, right? Like, how do we weight average things? I think the authors, like, there's a bunch of performance comparisons in the paper. So if you have like detailed questions, you should look in the paper. But I think like measuring an average performance is kind of hard because that very much depends on like which kind of device or which field you're going to use that. Yeah, so the authors showed the performance on a bunch of different data sets. I think I highlighted it here, and they have like specific performance for each of these data sets. And as far as I know, some of these data sets are mostly high memory intensity, some are low and stuff like that. So if you had detailed questions about that sort of thing, you'd have to look at the detailed figures in the paper. I don't remember. They definitely looked at all kinds of tasks.
Okay, thank you.
Yeah. Questions? Okay. Okay, so in that case, we can sort of go over into a bit of discussion. So I have some, so in case anybody else has like, but that would probably be in sort of in regards to questions. I have some jumping off points that I thought were kind of interesting. And one thing was, let's actually start with this one. Okay, so let's say we have a system that implements a sector DRAM, and we're now writing a program or a compiler for this sort of system. What sort of things might we now care about that we don't care about with normal DRAM? So what things become relevant for us to consider when writing a program, or more realistically, a compiler that weren't relevant for normal DRAM? Any ideas? So specifically about memory layout, maybe like normally what aspects of memory layout do we care about, and how does sector DRAM maybe introduce something else that might be relevant? Yeah, thank you.
I mean, usually the compiler cares about a lot about locality and tries to adjust memory in such a way, or put variables in such a way that they're actually close in memory.
Yeah.
So that they fill the cache line.
Mm-hmm.
I guess with this, we don't have to care that much about this if, under the condition that we actually request the correct sectors.
Yes, and so that's kind of true, but like a cache miss is still a cache miss, so that's still bad for us. It's just less bad. But what we might also care about is that we have certain data always loaded into certain sectors, for instance. So if we have, because okay, I won't go all the way back because it's like 200 clicks. On the one hand, because of how sector prediction works, so if we have some consistency of always accessing the same sectors, that's helpful for how this system works. And because if we have data that's spread across different cache rows, but always in the same sectors. So for instance, that might help with how we access memory. If we only have to, when we activate a row, so we don't care about an entire row, and there's different data in a row. And if we have all of the data in the same set of sectors versus spread across several sectors, that's more efficient with the way sector DRAM works.
Wait, you just said it was more efficient if we store data in one specific sector or in the same sector?
The sectors, yes, yeah.
How come that be?
Because we don't need to. So a row is basically because we don't. So if we have data stored in a row, in the same row, but we have it spread across. Maybe I do go. So a row is way larger than a cache block, for instance. And if we have data stored all in the same row, but across different sectors, so we have one cache block where we access data that's stored in, so all of the data is, okay, let me start fresh, sorry. All of the data is stored in row 100, and there's several cache blocks in that row, and we then care about several cache blocks, and one time we look at data that's in one cache block and it's stored in sectors 1 and 2, and then we look at a different cache block in the same row and it's stored in sectors 3 and 4. Then in that case, before we activate that row, which contains several cache blocks, we have to activate sectors 1, 2, 3, and 4, because that's the way we would do it. We would activate the row once with sectors 1, 2, 3, and 4, and then issue read commands that read a cache block that's stored in sectors, or a cache block, and then access the sub data that's stored in sectors 1 and 2, and then a different cache block stored in the same row, and then access the information that's stored in sectors 3 and 4. But if we, in both cache blocks, store that relevant data in sectors 1 and 2, then when we initially activate the row, we only have to activate sectors 1 and 2, and that makes things more efficient. Does that explain it?
Yes.
Thank you. Okay. Okay, yeah, now I'm just all of the way here. So one very simple question is, okay, so I said most chips have, most DRAM modules have 8 chips, and each chip has 8 banks, but that's not always the case. So if we implement a lot more banks, from the things I have showed you, what's one potential scaling issue we might face? I can try and go back to the slide, so maybe we can have a look at, okay, this is truly infuriating. Maybe I do it like this. I go all the way back to, with these sort of commands, what is maybe like one of these commands where the number of banks is relevant for how the command works. I may not have explained that very well. So the pre-charge command, in the pre-charge command, the way sector DRAM changes the pre-charge command, something we do is we implement which sectors we want to have opened with for the next activation command as part of in some of the empty bits here. But if we have a lot of more banks, then the pre-charge command needs more bits in and of itself, and then we don't necessarily have the same sort of leftover information that we could use. So that becomes more complicated. It doesn't derail the idea. We can either issue several pre-charge commands, one after the other, or we can just implement a new command that would then lead to a change of the memory and processor interface, which is one of the things we previously didn't have to change, and which the authors also cared about not changing. But yeah, it would also still work, but it is a potential scaling issue. Okay, I think I'd be done at this point, unless there's any additional questions, comments. I don't know. How much time did I take? Oh yeah, I'm also over time kind of. So yes, very much so. Then I'm very much done at this point. Yeah, thank you for your attention. And that's my talk.
Okay. Yeah. Can you hear me? Cool. Okay. Can I move this?
Hello, everyone. Hello. Yes. So now we're moving to the second presentation. Presenter is Konstantinos. Konstantinos is a first-year master's student, and he got his bachelor's degree from the University of Athens. He's interested in computer architecture, and specifically his research interests lay with memory management and address translation. Feel free to start.
Thank you very much, Mail. Can everyone hear me? Yes, okay. So my name is Konstantinos, and I'm going to be presenting functionally complete Boolean logic in real DRAM chips, experimental characterization and analysis. This is going to be the outline of my talk. I'm going to start with some background. I'm going to give a general idea of the paper. I'm going to go into details, and we're going to look at strengths, weaknesses, and the discussion. First, let's see some background. We have seen this many times in the lectures, but this is a DRAM module. It consists of DRAM chips. Each chip has input-output circuitry and an array of banks, which are all connected with this circuitry. And this is the bank. We have a lot of subarrays and a lot of sense amplifiers, and each subarray has its own local row decoder. Specifically, this paper focuses on this region, the orange region, which is the array of the sense amplifiers that is between two neighboring subarrays. Now, DRAM manufacturers, in order to increase the capacity of DRAM, have employed a new architecture called open bitline architecture, which looks something like this. This means that from the bottom subarray, column 0, 2, 4, etc., is connected to the sense amplifier from the bottom part, and from the top subarray, column 1, 3, etc., is connected from the top part. This way, we have half of the sense amplifiers that we have otherwise. But we face the problem that how is this going to work? We are connecting the sense amplifier, both the top subarray and the bottom subarray. So when the top row is activated, we have to make sure that we cannot activate any row from the bottom subarray so that we don't have interference. Essentially, the top data will be negated. So we do not want to touch the bottom connectors in any way. So we do not activate any row in the bottom subarray. So just a little foreshadowing, this looks like a NOT gate, but we're going to see how this is going to work later on. So let's see at the DRAM operations, all the DRAM operations. We have our subarray, we have our sense amplifiers, and the first operation of DRAM is the activate operation. We choose a specific row, and we fetch the data and amplify them into the sense amplifiers. The second operation is read-write. We connect a specific column of the sense amplifier to the input-output circuitry. And finally, we have the pre-charge command, which actually prepares the bank for the next activation. Usually it's done before the activation because we want to have the data as much as possible into the sense amplifier to issue read and write commands, as many as possible. So between these commands, we have some specific time constraints. So the manufacturers have said that we need to keep a specific amount of time between each command, and this is going to play a role later in the presentation. So let's see what this paper is about. First of all, let's look at the motivation. We know that data movement from the lecture is a really big performance and energy bottleneck. And previous work has shown that processing using memory operations can alleviate this problem. We can do the processing in memory and not have all the data movement that we would normally have. So the problem is that current work in processing using memory, and especially the ones that focus on commercial off-the-shelf DRAM chips, lack the NOT operation. The NOT operation has not been shown. Lack the NAND and NOR operations, which also have not been shown. And despite having AND and OR operations with 2 operands, we do not have AND and OR operations with multiple operands. So this work aims to propose mechanisms for these operations, leveraging the open bitline architecture that we saw. And they will evaluate these mechanisms with 280 DDR4 chips from 3 different manufacturers. And these are some preliminary results of the self-DRAM chips perform NOT operation and multi-input operation with more than 94% accuracy. And this is shown in commodity chips, which is really important. Let's look at the key mechanism quickly. First of all, they show how to simultaneously activate rows from 2 neighboring subarrays. We're going to see that in detail later. The NOT operation in of the self-DRAM chips and the multi-input operation in of the self-DRAM chips.
But in order to understand exactly the mechanisms, we need to know how they experimented on the DRAM chips. So this is the testing infrastructure. It was used before in DRAM Bender. It's based on this work. And we can see that we have a host machine, a desktop essentially, an FPGA board, which controls the operation of the DRAM and controls the DRAM and the timings in which these commands are issued. And we have a DRAM module. Clamped onto it are some heating pads, which essentially heat the DRAM to the temperature that we want. And we control this temperature through the temperature controller, which has probably a thermostat and detects the temperature and regulates it. So the authors tested 208 DDR4 chips from 3 manufacturers, as mentioned before, with a plethora of parameters, speed rates, chip densities. We're going to see them later. But the DRAM manufacturers were SK Hynix, Samsung, and Micron. But not every manufacturer supported every single operation. As we see, SK Hynix supported both operations, both NOT operations and multi-input operations. Samsung supported only the NOT operation that the authors proposed, and Micron didn't support any of them. Now, the authors do give an explanation about why this happens. It's actually a hypothesis from a previous paper that says that when we violate the timing constraints, I talked about the timing constraints before in the commands, when we violate these timing constraints and we put commands really close one to the other, we can see that sometimes the chips do not even issue these commands. So the Micron chips do not issue some specific commands if some timing constraints are violated. So essentially, we cannot do these mechanisms because we cannot issue the commands in the correct timing. Now, let's focus and see the heart of the paper, which is essentially the key mechanisms. And we saw before, there are 3 key mechanisms: simultaneous Mutlu activation, the NOT operation, and multi-input operations, NAND, NOR, and OR. We're going to look at them in detail, and then we're going to have some small results for every single one of them. First of all, simultaneous low activation. This actually is necessary in order to build up the other 2 operations. So we have 2 neighboring subarrays. The first step is we need to activate a row from subarray X. We activate row A. Then, as normal, we need to pre-charge the specific row, but the manufacturer actually has proposed a specific timing window in order to do that. The authors violate this timing window. So they do the pre-charge command really close to the first activate command. Next, we have an activation in the other subarray. And again, we do not keep the proposed timing by the manufacturer, we violate it again. So what we have is 2 violations of the timing constraints, and this mechanism supposedly will activate more than 1 array from these 2 neighboring subarrays. So in order to understand exactly how this mechanism works and which and how many rows were actually simultaneously activated, the authors did all the combinations of row A and row B. So they tried with every row from subarray X and with every row from subarray Y. And they noticed they had some observations. The first observation they had is we can simultaneously activate multiple rows from one subarray to another from 2 neighboring subarrays that are close by, that are neighboring. The second observation was that these activations had a specific pattern. This means that when n rows were activated from the first subarray, exactly n rows were activated from the Y subarray. So we had the 1-to-1 ratio. This was the first activation pattern, it was very distinct. And the second one was when n rows were activated in subarray X, twice as rows were activated in subarray Y. That means we have a 1-to-2 ratio. And these patterns were so distinct that they had a notation. And the authors gave this the name n-to-n. And to the second one, they gave the name n-to-2n. And it's important to keep that in mind because the key takeaway that they had from these observations was that when we had the n-to-2n pattern that we just showed, the number of n, the maximum number of n was 16. That means that a maximum in 2 neighboring subarrays, we can activate 48 rows simultaneously, which is a really interesting result. And I'm going to say why I find it interesting later in the talk. So once we have this done, we can move on to the actual mechanisms that perform the useful operations. First of all, we have the NOT operation. So we have 1 cell from the first subarray and 1 cell from the second subarray. We suppose that the source cell is charged to 0 for this example. And first of all, we activate the specific row. We see that at the beginning, we know that the connectors have a voltage of VDD over 2. Then we pre-charge without violating the timing constraint. So what we notice is that the top connector has a ground because the source was 0 before. So the top connector has a voltage of ground. And because the bottom connector has the negated value, we see that it has a voltage of VDD. Under normal DRAM operation, this doesn't affect the destination cell at all because we haven't activated anything and the voltage doesn't pass to the destination cell. But the authors issue an activate command and they violate the timing constraint. That results in the cell slightly charging and charging and charging. And finally, when we issue the precharge command, the destination cell is fully charged. As you notice, the source cell has been negated to the destination cell. We have a NOT gate. And it's in DRAM. And they tried to experiment with this. So they did a sweep of the parameter space. They tried so many chips and they tried different row numbers. They tried different temperatures, different number of destination rows, different distances from the sense amplifier, and different speed rates, die sizes, and a lot of other parameters. So let's see a little bit some results for this specific NOT operation. Now, we start with defining the success rate. So the success rate is the number of successful attempts divided with the total attempts. So if we make 100 attempts and 10 of them work, we have a 10% success rate. Let's kind of explain the box chart, which is a complicated chart. We can see that this is a number of attempts with different success rates. And the small little circle is the mean of all the attempts. The line is the median of all the attempts. And the top, the box contains 50% of all the attempts, which is the majority of the attempts. And the bottom and row line is actually the maximum and minimum. There are some outliers as well, but they're considered outliers. There are a small amount of them. So let's look at the trend. So as the number of destination rows increases, we can see that the success rate drops. But despite having this effect, it makes sense because we have more destination cells, then the sense amplifier will not be able to charge all of them, up to 232 of them. But we can see that in every case, there is at least one cell that is successful, that has a success rate of 100%. That means at least one cell in the entire subarray can perform a NOT operation. Then we see the temperature. The temperature, and this is a really positive thing, the temperature doesn't affect the operation at all. So even in a high range of temperature, for 50 to 90 degrees Celsius, we see a 0.2% variation. And specifically in the 32 row case, which is the worst case for the NOT operation. Then we see the speed rate. The speed rate is chaotic. There is no trend to the speed rate, and it's an interesting result. We can see that in this specific case, when the speed rate is low, we have a range of success rates. When the speed rate becomes bigger, it's the medium speed rate of the three, we see that it's the worst, it has the worst success rate, and in the biggest speed rate, the success rate for some reason increases. And this is all for the NOT operation, and we're going to move on to the multi-input operations. First of all, in order to multi-input operations, we need to have some cells in the top subarray, which we call the reference subarray, and we set them in order to set the operation. And the bottom one is the compute subarray. We put our operands in the bottom subarray one by one. Now, the initial setup is that we charge one cell in the reference subarray as 1 and one cell as half. Now, this half charged cell may seem weird, but it's proposed in a previous work called frac DRAM. And actually, in commodity of the self-DRAM chips, we can have a cell that is half filled. It's neither full nor empty, but it's half. And the authors leverage that to perform the multi-input operation. So we activate both the top, all the cells that you can see. We activate all the rows that you can see, and we violate the constraints between them. So we activate the top, we precharge, we activate the bottom, all violated time constraints. And we notice that in the connectors, we have the average of all the cells. So the average of all the cells in the reference subarray is 3VD/4 in this specific case, and the bottom one is X plus Y/2. Now, depending on what the value of the voltage is, we can have two results. If the average in compute subarray is bigger, we can see that the voltage is dropped downwards. That means that the sense amplifiers pull the voltage downwards towards the compute subarray. If the average is smaller, then the sense amplifiers pull the voltage upwards towards the reference subarray. And thus we can differentiate between a 1 and a 0. Let's see it in a little bit more detail with a truth table. So we take the exact same setup, and we see that X and Y is 0. In this case, we see 0 voltage at the bottom. So the voltage is pulled upwards. Again, in this case, y is 1. Again, the average is not bigger, so the voltage is again pulled upwards. Again, with x only 1. And with x and y equal to 1, the voltage this time is pulled downwards. We can see that the average is bigger, is VDD in this case. And what you may have noticed is that the reference subarray is an AND gate, and the compute subarray is an AND gate. So we have successfully done an AND gate and an AND gate. And the same with the OR gate. I'm going to focus on the setup mostly. We can see that in the reference subarray, we have one cell that is completely empty and one cell that is half filled. And we can see some examples. If they're both 0, if x and y is both 0, both the operands, we can see that the average at the bottom is 0, so the voltage is pulled upwards. If only y is 1, the voltage is pulled downwards. The voltage at the bottom connector is more than the voltage at the top connector. And again, when x is 1 and when both x and y is 1, again, the voltage is pulled downwards. And as you have noticed, the reference subarray is an OR gate and the compute subarray is an OR gate. So we have both an OR and an OR gate. But what about multi-input? I'm showing 2 inputs through this entire presentation, but there's the setup. I'm going to show specifically the setup. And for the end reference subarray, we have to fill all the cells with 1 and 1 cell half. So if we do that and put our operands in the compute subarray, we're going to have an AND or AND gate. And about the OR, we fill all our cells with 0, except from one that we fill it halfway. This way we can have multi-input AND, NAND, NOR, and OR operations. So let's see how the authors experimented and what were the results. How robust is this operation? So again, they shown different row numbers, different temperatures, different number of destination rows, different distances from the sense amplifier, and different speed rates and die sizes, again. And these are some of the results. Let's begin with the number of operands. Now, this is a counterintuitive result. As the number of operands increases, then the success rate rises. Now, this is interesting and happens because this mechanism's problem is when the voltages are close, the voltages at the top subarray and the bottom subarray are close, the sense amplifier cannot sense the difference and cannot pick which subarray the voltage will be pulled to. So when we have more operands, we have more opportunities, if you think about it, for this distance to be smaller. So many cases in the 16 number of input operands case have a bigger difference between the compute and the reference subarray. So that's why this is detected more easily and the success rate increases. Let's see at the temperature. The temperature again has minimal effect on the robustness. So these operations are really robust in terms of temperature. We can see from ranges to 50 to 95. We see small variations, mostly in the OR and NOR case, when we have 2 operands. So this plays almost but no significant role. And finally, the speed rate again is chaotic. There's no trend. We can see here, we see a smaller difference between the medium and the low and high speed rates. We see a bigger one here. And for some reason, in the NAND gate, there's no difference. The speed rate doesn't play any role and the success rate is up. So to conclude, the authors had 3 major contributions. They simultaneously activated multiple rows from 2 neighboring subarrays, and they managed to activate up to 48 rows. They managed to do the NOT operation in off-the-shelf DRAM chips with a success rate on average of 98%, and they managed multi-input operations with a success rate of 95%. Now, this is all for the mechanisms. We're going to move on to the strengths and weaknesses, but if you have any questions, please tell me. Wait for the microphone.
How easy is it to control the VDD by 2 volt voltage in a row? I think that was used for the NAND and OR NOR case.
What do you mean how easy it is?
I'm assuming that you need some specific access pattern to set a VDD by 2 voltage in a row.
Yeah, the details are more on the FRAC DRAM paper. I'm going to scroll through the slide, but the details are in the FRAC DRAM paper, but needs a series of operations in order to have this half cell, similar to these operations in this paper.
Could it be better to do, for instance, if you wanted to do a two-row operation, and you need a 3 VDD by 4 on the reference subarray, could it be better to have 3 rows of VDD and 1 row of 0? Would that possibly give you a more reliable 3 VDD by 4?
This could possibly work, but this is also one of the weaknesses of the paper that we show, that I will talk about later, is the fact that these are extra rows. These are not rows of operands. So we're taking that, and imagine this row is 4 kilobytes wrong. So you're sacrificing 4 kilobytes just to have more. And the half in this case plays a really important, plays a really neat role, because it allows this whole thing to happen. If I think it would work, Ismail might have to correct me, but I think this might work. But I don't know how robust, and if it's going to be more robust in this case, or if you have FillSL.
I see.
Yes.
Thank you.
I would consider it even being more robust, but who knows? Anything else? Any other question? Please. Here.
So I still have a question. What accuracy refers to? Is this like per bit or per word or per line?
The success, it was the success rate, right?
Yeah.
So the success rate is if we're doing X total attempts for this specific thing. I think for cells, we're looking at the cells specifically. If we do X attempts, we see which of these attempts the cells were correct. So we count cells essentially. We count how many cells we did the operation to and how many of them were correct. So this is essentially the success rate.
I have one more question.
Please.
Do we copy data into these rows to perform computation because it's destructive?
It is destructive, yes, and this is another weakness of the paper. And we do have to do some form of copy. We need to keep our data twice.
Like something like row clone?
Something like row clone, or the CPU can actually put the data twice, or leverage row clone. They don't leverage row clone, but it could be that.
So in that case, it would be safe from retention concerns, or I mean, leakage concerns of these rows, because the reference value has to be quite accurate for you to perform good reliable computation.
Yes, there are issues with robustness, obviously, because the average is more than 98 and more than 94. It's not 100%. So the fact that you copy the row, I don't think has anything to do with the mechanism. The fact that you keep the copy there, it's mostly in the total sense, in the fact that you have to put the rows somehow there in the correct place, in the correct rows. So I don't think it helps with success rate. But still, success rate is not 100%. And when you are doing computation, this needs to be taken into account. Yeah. But still, it's a really good number for a NOT operation. Any other questions? No. So let's move on to the strengths and weaknesses. First of all, the strengths. It was the first paper that introduced functional completeness in DRAM, in off-the-shelf DRAM chips. In DRAM chips that we can buy, there is functional completeness if we violate the timing constraints. As we saw, they showed not multi-input NAND NOR gates that didn't exist, multi-input gates that didn't exist before. Also, they had a really thorough experimentation setup. We saw that they did a sweep of the parameter space. They checked so many chips. They checked 280 chips with a lot of different parameters. So their evaluation was very thorough, very solid, and they showed that these things can actually happen in commercial chips, in commodity DRAM chips. Next, something that I found really interesting is the fact that in order to do their operations, they introduced a way to simultaneously activate rows from two neighboring DRAM subarrays. And this mechanism can be leveraged not only for this mechanism, but for other different mechanisms. Maybe for a copy, maybe for all of this. And I think this is gonna be a really good tool in the hands of a DRAM researcher in the future. And finally, they did no modifications. Previous works have shown how to modify DRAM and have an operation with modifying the DRAM, but this work did it in commodity chips. And I think this is really important for demonstration purposes. But let's move on to the weaknesses. First of all, the methodology has significant memory overhead. We can see that for every operand, we need an extra row. So, and these rows are, as we said, maybe 4 kilobytes, they are long. So we're sacrificing this space during the computation in order to have these extra rows that actually serve us nothing. And we have to initialize them. And it's a general hassle, the fact that we have to have all these extra rows. And also, after computation, the data that we had in the compute row, as you mentioned, is destroyed. The result overwrites the data, both in the extra rows and the compute node rows. That means that all our setup in the extra rows and all our operands in the compute nodes are gone. So we have to copy, we somehow copy and rewrite them, and it has a memory overhead. That's the definition. Then it has an intuitive input format. What do I mean with that? First of all, because we leverage the open bitline architecture, we saw that, for example, at the bottom, the columns 0, 2, 4, and so on and so forth are connected to the sense amplifiers. That means that our data need to be put there in order to do the computation. What happens to the other columns, though? They're underutilized. Maybe we can put something there. Maybe there are a lot of uses, and I'm going to have them in the discussion, but these are not used for the computation. So we have half the row to use to do actual computation. And then we need to have this format somehow. We need to take our data. I have disconnected this row. And so that if we have our data in this format, we need to do this conversion. We need to take the data and spread them around. And this needs to pass through the CPU, or we need to change the DRAM in order to do this conversion. But still we have a penalty. So I think this is a real weakness of the paper. And then it's not applicable to all manufacturers. They gave an explanation why, a hypothesis why to be exact, but it's not applicable to Samsung and Micron manufacturers. And the Samsung, the node operation is supported by Samsung. But I mean, this is a strength and a weakness because it was mentioned in the paper. It was mentioned the fact that these manufacturers, we cannot make it work. And we tested it and it's not possible. So it's a strength and a weakness. And finally, the speed rate doesn't make any sense. Why does this happen? Either there is a huge correlation with the speed rate, so these operations are either really sensitive to the speed rate or have nothing to do with this. And this is just statistically insignificant, just randomness. But in NAND and OR, it plays a huge part. In NAND, in many operands, we see it plays no part. It is weird. Are there any questions about strengths and weaknesses? No? So we move on to the discussion. Okay. So first of all, what are other operations that can be implemented using the same open bitline DRAM mechanism? We have a bulk way to do these operations. We have this NAND, these OR gates. How can we leverage them? How can we leverage them differently to do useful computation? Any ideas? No, I didn't suppose so. Okay, so I would propose bulk value initialization. We can put our values in the X operand, and we can leverage our trusty NOR or OR gate, and we can do it. We can copy the result in many rows, 32 to be exact, in maximum. So, and we can do it in a bulk way. We can do it for many columns. So bulk value initialization could leverage the open bitline in order to do some useful computation. Then, how can the operations presented in this paper be orchestrated on the CPU side? Now, this is a big question. It is based on SIM DRAM and MIM DRAM. How can we do a similar architecture? We presented, I think, MIM DRAM 2 weeks ago. How can we do a similar architecture in order to also orchestrate these operations? And how would the operand movement look like? How could we move the operands to a specific place? We said row clone. Anything else? How could the operands be allocated? When the page fault happens, we need to know this place is for operands. How are we going to do that? How are we going to signify to the OS that? No idea. How could the programming model look like? How would the ISA look like? How can we do the data formatting? I mean, SIM DRAM and MIM DRAM have a component in the memory management unit, in the memory controller. Please.
It could be quite similar to.
No, continue.
It could be quite similar to MemDRAM. You could just have it done at the memory controller where you move the data, you unpack the data into the format relevant for. What's it called?
So when we throw something off the cache, the conversion actually happens at this specific place, and we flush the caches, and the format takes place at the memory controller. Yes, exactly. Yeah. It could be done there.
For the operand allocation, do you mean doing it Do you mean like what rows in the subarrays, or?
Exactly. How we're going to put the rows, and how is the CPU not going to put data there? Because in order to do the computation, we're actually reserving some specific rows. How are we going to do that?
The memory controller again, because you need to know the address mapping, right?
Yes, is the memory controller aware of the address mapping? So we need somehow to communicate to the memory controller that this is the address mapping, this is used for computation, this is used for in-DRAM computation. It would be interesting. Please, you have the question.
Yeah, I think I had a similar input, but maybe an idea would be like to reserve a whole bank just for the operations, and then use it a bit like a vector register.
Yes, this is overdoing
that's wasteful, I guess.
Yes, it's overdoing it because we actually reserve an entire bank for as long as our computation, or maybe forever, depending on how you're going to reserve it. But yes, this could be really interesting. Yes, please.
I would guess, just as in the MemDRAM paper, one could use operating system support to block certain parts of memory as computational or relevant for computation based on what the program runs. So depending on the operations, one could have certain rows as off limits, and thus enable like not as much of a big memory overhead as preserving an entire bank, for example.
Mm-hmm. Yes, but and I have a follow-up question on that. Do you think you should integrate these operations in the SIMDRAM model, or do you think they require a different? Because they're special, the operations used in SIMDRAM, MIMDRAM are a majority, and we have changes in DRAM. Do you think we should integrate these operations inside the same architectures, or should we have a different one?
I mean, one could use the same ideas as in SIMDRAM, since most of the operations are similar, and probably the way you would compute things would also be similar. I'm not quite sure about whether like the specific control structure, like the ISA extensions, how well they would map to exactly this. Mm-hmm. But in general, yes, the data layout could be like similar to SIMDRAM. Maybe one would have to adjust for the like slide spread, as you mentioned, but that should not be like huge work.
Yes, you're right. Yes, it could be done. Anything else? Okay, so the next point is, how can we leverage the unused cells? We talked about it. How could the unused cells, the half of the cells in the row, could be leveraged? Any ideas? Maybe save irrelevant data, or we could split the data in half. We could do the entire computation in the row. We could put half the data in the actual computation, and then put the rest of our data in between and do the computation with the subarray below. We didn't put the subarray below, but we could do that and actually take advantage of 3 neighboring subarrays and do the and use all the row if possible, because the subarray in the bottom is connected like the subarray on the top in this graph. So the other columns are connected with the bottom sense amplifiers. So we could leverage both of them, possibly. And finally, how do you think the evaluation of the mechanism in real workloads should be tackled? Is this more energy efficient at the end of the day? Is this more performant? How could this be tackled? How we should evaluate this? Or any specific domains that this could work? No? So this could work maybe on genomics, on graph processing applications, something that can be highly parallelizable, embarrassingly parallelizable. And yes, and I think there is a lot of application. I think this could be a really interesting thing to evaluate, whether there's actual energy gains to be had. And with that, I wrap up the presentation. Thank you so much for your attention. but now. Any comment, Ismail?
I'll maybe ask a question to you, actually.
Please, please.
Can you go to your last discussion point? No, maybe the third one then. So you propose to use half of the cells and the bottom subarray and place data there. Where do you put the reference cells?
On the bottom, on the other subarray, on the third subarray.
Okay. Does that really increase the utilization, or is the underutilization coming from the fact that you have to have reference cells?
Yeah, the thing that it actually helps with, because it has a destructive nature, either way you were going to put data in your reference subarray, in this reference subarray, if you did twice, if you move data. So the only thing that you gain is the fact that you move the data once. You put the data in the middle rows, you put them only once. So you don't have to copy. Because it has destructive nature, you were going to form two reference subarrays either way, either serially or parallelly. So then you just save the time to do the formatting and to put the data twice there.
Okay, fair enough.
But so one, not sure if I understand the open bit line correctly, but when you have data in the cells in between, and when you perform the activations for all of those, won't your data get corrupted in the cells in between?
But you're going to have no, and I don't think they're going to get corrupted. I'm not sure. I'm not 100% sure of that.
There's a bit line running along, right? Or am I mistaken?
That's true, but I don't think they're going to get corrupted if you don't, because you're not having a sense amplifier connected at this point, at this column, at the specific column.
Okay.
So I think the data is going to be put on the sense amplifier, amplified, and then put back on the cell normally. I think.
Okay. My intuition is that I would just average all the values in those cells, and then
there's no connection between the columns.
No, the one single column.
Yes.
So let's say you're activating 4 rows together. The 4 cells, all of them have different values.
Yes.
And they're connected by the bit line, right?
Yes. That's the mechanism.
Right. So the 4 values, the bit line will have the voltage of the 4 voltages on an average. Won't that affect the value?
On the columns, we have the operands. The problem is the other column, the next column, which is not connected to the operands column at all.
Okay. I'll think about it again.
Anything else?
You want one more?
No. Please.
Okay. I think you asked this question also. Maybe it was not quite clear, your answer in that case. To ask it simply, how do you make sure the value, the voltage value, half VDD, is maintained at half VDD for the cells that you initialize with using fractional operations?
I'm not really familiar with frac DRAM that much, but I think it's maintained in the frac DRAM paper. First of all, we don't know that it's half VDD. We take it in a side channel way, the fact that it's half VDD, but I think it was kept. They checked it exactly after by not violating the time constraint. So if you do it last, maybe it will last. It will last long enough to do the computation. Yeah, and it's not also 100% half VDD, I think.
Yeah, that's. I think that's the idea. Also, you do it right before you start your computation, so you want to make sure half VDD is almost.
Okay, I want to ask an open-ended question. So now you see all this functionality in the commodity DRAM chips, and we can get benefit out of this, right? So now assume that you're designing the next generation of DRAM chips and you can do modifications. So what kind of modification would you do to make these operations more useful and more reliable?
These specific operations? Or other operations that are functionally complete?
Well, if you're interested in other operations, you can talk about them also.
Okay. I think it would be more beneficial to do a majority operation. I think if we change the DRAM, we should do a majority operation. But if we don't change the DRAM, we want to increase the the success rate of this specific one, first we need the way to put reliably half voltage on a cell, which is difficult in itself. I think it would be a really difficult modification to do. And then we will need to have sense amplifiers that actually amplify the difference better. If there is even the slightest difference, they will need to pull at the correct point. I think that would be the two main changes. Yes. Anything? Thank you so much again. Oops. Yeah, thank you.
So I'll say a few words about sector DRAM. I did not prepare for this, so I'll improvise. That paper is not the first or the only paper to show that we don't use all of the data we fetch from main memory in our processor systems or processor-centric systems. But it is kind of surprising that we haven't done anything to fix it for a very long time, in real systems, I mean. As far as I can remember, the paper that we wrote, the initial versions of it at least, or the earlier versions got rejected 2 or 3 times from major conferences. And the reason never was, oh, you are not fixing the problem that you showcase here. It's always like, how will this work with cache coherence? How will prefetching affect it? Which are, I consider, auxiliary sort of smaller problems that you have to introduce whenever you propose a new technique. And then work that follows your work might fix that, right? So, I mean, to summarize, I guess, I'm a bit sad that nothing has been done to fix this inefficiency in real systems, as far as I can see. And second, when you change a lot of things, like Lorenz mentioned, like sector DRAM does, you face a lot of resistance from reviewers specifically. So be careful, I guess. Okay, that's the things I wanted to say. Do you want to add anything to that?
Yeah, I don't know. But still, you can change a lot of things. That's how progress happens. If you don't change anything, there is no progress. I'll make a comment about maybe this. So I was surprised that you didn't put making this reliable as a direction like Giray mentioned. Is that not interesting? Clearly you have concerns about reliability.
Yes, there are concerns about the reliability, but I think the architectural part is more important. Because if we cannot orchestrate and integrate it with actual workloads and have a way for the entire stack to propagate and have real computation in real DRAM chips, then the reliability part can. We saw that it's quite reliable, and if we do some minor modifications, we can assume that we can go to 100% reliability.
How do you know?
I don't.
Okay.
But I would consider that would be easier than actually integrating this in the entire stack. That would be my argument, but I don't know if it's correct.
Usually, the last mile is the hardest to walk.
That's true. Yes, yes. But also integrating into every single program that the users use throughout the world is also quite.
But you don't need to integrate into every single program, right? You just need to show benefits in some important ones.
That's true. Yes. But still, a way to program would be interesting because these are just violating the timing constraints with an FPGA board.
Yeah,
it's really important, but it doesn't show the use inside the into the workload.
Yeah. Yeah, but I think the interesting part of this work is really demonstrating that it's possible in existing DRAM chips.
Yes.
I think later work should really take advantage of it and show how to make it reliable, how to make it usable. And these go hand in hand, probably.
Robustness is important as well.
Yeah.
Yes.
Okay. Anything else? Otherwise, we can end here. Cool.